Alright, so in this video we'll talk about the resultant of two vectors. Resultant of two vectors, as we've already discussed in our previous videos, is, so if you have two vectors A and B, the resultant, which we call by R vector, is the addition of the two vectors. Now, graphically, that means invoking the triangle, the triangle rule of addition of two vectors. That means if this were our first vector, a vector of, say, some length, say 3 units, pointing in the east direction. So let me write that down as well. Pointing in the east direction, E for an east. I can draw out east, north, and that gives me south and west just on the side. And let's have our B vector to be pointing in, say, 45 degrees from the A vector. That means let's suppose that the B vector is, say, 4 units, and it points in the northeast direction. So northeast direction means it's in this, and that we assume that this angle is 45. Therefore, if this angle is 45 and the angle of A is, well, east, which is 0, because A is at 0 degrees from east, B is at 45 degrees from east, and therefore the relative angle between them, let me take another color, would be, you guessed it, 45. So it comes from 45 degrees minus 0 degrees, so that's 45 degrees. But more importantly, what was our intention was to draw out the resultant of the two vectors. Now, resultant meant completing the triangle, and that was done by joining the base of A to the head of B, and that was our R vector, or the resultant vector, which turned out to be A plus B. Now, this is in vector notation, so you constantly just add R, add A and B to get R, because if A is 3 and B is 4, then R cannot be 3 plus 4 equal to 7. You know, it cannot be the case. And the reason why is because the vectors these are vectors, you constantly add them up. Even if you do add the magnitudes up, that doesn't make sense, because say this is 7, I agree with you, even though that's a mistake. We don't know where exactly R is pointing. This application is kind of flawed. This mathematical operation is flawed, and regular addition doesn't really work with vectors. So this here, even though this seems like a mathematical addition, is actually vectorial addition. So it's a different application. And you would have guessed it by now that because vectors are special entities, we constantly deal with them in terms of numbers. We have to really change the mathematics. And we change the mathematics in many other ways. We actually define a product of vectors in 2 ways. And by product, I mean the multiplication sign. Well, that's something for another video. But as in this video, what we try to do is we try to evaluate 2 properties of R. Now, since R is a vector, right? So if it's a vector, it must have a magnitude and a direction. What we try to do is we try to investigate both those properties. That means we want to find the magnitude of R, which is given by the modulus. We want to find the magnitude of our resultant vector. This is something that we want to investigate. And second thing we want to investigate is the direction of R, and that is given by R hat, which basically tells you in which direction it's pointing. If we are able to somehow figure out the direction which R is pointing, and we know the magnitude, then we know every single detail of the vector R. And we hope to do that just by knowing these 4 properties. The fact that A is 3 units, we know the magnitude and we know the direction. And same with B. We know the magnitude of 4 units and we know the direction in the northeast direction. So with all this information, we hope to find R, right? So let's kind of move ahead now. All right, so let me just erase these objectives a little bit and erase this just to kind of clear out the space. And let me do one thing. Let me draw perpendiculars from this point. Now, if I call this O, this point as O, I call this point as A, let me call this point as B. Now, this forms a triangle. So OAB is a triangle. That's because we invoked the triangle rule. But more importantly, what we can do is we can actually draw perpendiculars from the point B. And when we do that, we drop a perpendicular to A. That means this angle here is 90 degrees. Let me just write down the properties of B vector, which I ended up deleting. So this is B vector. This is, let me write it here. So this B vector is 4 units and points in the northeast direction. And A vector, well, is 3 units in the east direction. So I can also get rid of this. Well, okay, let me redraw A bit. That is my nice looking A vector. All right, so if I drop the perpendicular from B, this is point A, let me write it again. Right, so now that I've dropped the perpendicular from B to the line of A, this is just the extension of line O, of the line segment OA. So this whole line is just an extension, right? So that means that we can call this point as, say, B prime. How about that? That should work. So we would try to look in the triangle OB prime B. Now, OB prime B is a perpendicular triangle, so right angle triangle. And one of the lengths, the hypotenuse, in fact, is R vector, or I could call this R vector's modulus, the magnitude. The base is not A. If this were A vector, well, the base is not just A, it's the modulus of A with this component, and this component is what we call as AB prime. So this is basically, this base here is, if I change my pen again just a bit, this base here is actually OA plus AB prime. So this is the length of my base. And the height here is, well, BB prime. So here, in this diagram, I have basically drawn on the triangle, which takes into account the modulus of R, something that we need to figure out, and the length of the base and the perpendicular. So if we know these two lengths, OA plus AB prime and BB prime, then we can easily figure out the magnitude of a vector R, the resultant of A and B. All right, so let's proceed. The first thing that I can do is evaluate AB prime. So OA, which is this distance, the length of the green vector, the length of A vector, is basically A vector's magnitude. And that should be, well, A vector's magnitude would be 3, right? So that would be A vector's magnitude. But we were trying to solve this case for a more general situation. So even though I'm writing this as 3, I'll still work with the modulus of A. And similarly, we will have AB to be the modulus of B, which would be nothing but, well, the modulus of B is 4. So this is 3 units. The modulus of B is 4 units. But take note that AB doesn't come in a triangle. It's not present in our triangle O, B prime, and B. So we really can't work with this directly, but we need to work with some other lengths. Let's try to work out what the length of AB prime is, and also the length of, well, BB prime. AB prime and BB prime do end up in our final triangle, so it would be really nice to have their lengths as well. And in order to do that, we must invoke our trigonometric identities. Right, so like I said, I want to solve this case for a more general situation, and in order to do that, rather than taking this angle to be 45 degrees, I would, for the moment, take this angle to be a more general theta. So this angle here is theta. This length is the magnitude of vector A. This length, AB, is the magnitude of the vector B. And we are now going to figure out the lengths of AB prime and BB prime. So AB prime, if you look at this triangle, AB prime and B, you would realize that that is also a 90-degree triangle. So if we know the hypotenuse, then we know, and the angle, then we know the base and the perpendicular. So the hypotenuse here is AB. So, and the base is AB prime. The angle is theta. Therefore, the length of AB prime would be hypotenuse, which is AB, multiplied by cosine of the angle, that is theta. So that would be, AB is, well, B vector's modulus multiplied by cosine of theta. So that's just cosine of theta. And likewise, BB prime turns out to be the perpendicular of the triangle, of the small triangle AB prime B. And by that, I mean BB prime would be, well, the hypotenuse, which is again AB, multiplied by, well, sine of theta. Now remember, sine always gives you the perpendicular, and cosine always gives you the base. So if you remember your trigonometric identities, this would follow. So AB prime again is B, the magnitude of B, the vector B, which would be 4. I'm not substituting it 4 here because I'm working for a more general case, but we can just work with B modulus, and sine theta remains sine theta because, well, it's a general angle theta, right? So let me just get rid of this for the moment. Therefore, now we are in a better position. Why? Because we know AB prime, we know BB prime, and we also know, well, OA. OA is the magnitude of A vector. So we have all the identities. Therefore, we can figure out what the value of our vector's modulus would be. Well, we know for one thing that it's the hypotenuse of this right angle triangle. Therefore, the square of this would be equal to the sum of the squares of the base and the perpendicular. That would be OA plus AB prime square plus BB prime square. We can work this out a bit more. OA, as I have already stated many times, is the magnitude of the vector A. And AB prime, as I've already figured out from this, would be the magnitude of vector B multiplied by cosine of theta. And we need to square that up. Similarly, BB prime would be, well, from here, would be the magnitude of B times sine of theta. But we must square that as well. So we have our expression for R. Let me just get rid of this because this is no longer required. It's just an explanation. We already have used that, so we can proceed ahead. So this is square. Therefore, let me change the color again. R square, R as in the magnitude of our vector, would be, well, we can expand this out. So this would be A vector's modulus square plus B vector modulus square cosine, well, that would be cos square theta, and we must add the cross product term, which would be 2 times A times B times cosine theta. So that's just the first expression, and we must add that to the square of this term. So that would be sine square theta times B square. Right, so it looks like a very ugly situation, but it can be reduced and can be simplified. Now, if you have a look at this term here and this term here, you see that they are of the form cosine square theta plus sine square theta multiplied by, well, B square. Now, you know that this expression within the bracket is always equal to 1. Therefore, this entire expression would be equal to B square, the modulus square of the vector B. Therefore, we can write this now as A square, the modulus square, plus these two terms give you B square plus the cross product term, which is A, B times cosine of theta. So that must be the value of R square. But if I want to evaluate R, which is the magnitude, the length of this blue side, OB, then I must take the root of this entire expression. So this is what I get as the value, the magnitude of the vector. So this is how we would work in terms of evaluating the length. Now, in order to evaluate the angle, that means we need to ask ourselves, wait, now that we know the length, can we figure out the angle at which R is oriented, say, from A? So can we figure out this angle? Let me call this, well, let me call this phi. So let me just get rid of this. Oops, yep, that works. This as well, that's being careful. We want to evaluate val phi. Now, how can we evaluate phi? Again, you can write down two equations for this. Now, since this length is the magnitude of r, something that we have already evaluated here, but let's ignore that for a moment. Then we know that b prime would be the magnitude of r times sine of phi. Remember, because this is a perpendicular. Now we're looking at the triangle OB prime B, and this is a right angle triangle. Therefore, we have this relation, and similarly, we can talk about the base, which is OB prime. OB prime would be, well, r times cosine of phi. So that's basically everything in terms of r and phi. Now, we know what r is from this expression, so the only thing we need to do is evaluate for for phi. So at this point, what we can do is we can substitute for bb prime in terms of the expression that we've already found out, and eliminate r, because we know what r is. So all we need to do is solve for for phi. I'm confusing theta for phi now, I don't know why. Anyway, with these two equations in hand, what we can do is we can divide them up. When you choose to divide two equations, you divide the left-hand side with the left-hand side and the right-hand side with the right-hand side. So we get r sine phi divided by r cosine phi should be equal to bb prime by ob prime. Writing that again, we can work out what bb prime is, as we have already done previously, where bb prime was the magnitude of b vector times sine of theta divided by this entire length, ob prime, which is a vector's magnitude, added to b vector's magnitude multiplied by cosine of theta. Right, now if you look on the left-hand side here, we have r and r in the numerator and the denominator as well. And this expression here is sine of phi by cosine of phi. If you again recall your trigonometric identities, that is nothing but tangent of phi. Therefore, we have another equation. Let me just get rid of this and write that again here. We have tangent of phi equals this. So this expression, which is expressed in terms of a and b, and the angle at which a and b are oriented amongst themselves. So these two boxes give us both the required values, the required expressions that we wanted to find out, that we stated in the beginning of the video. The first, well, let's look at the second box here. Well, the second box gives us the magnitude of the resultant vector, something that we wanted to figure out. And this here would give us the direction. The reason that gives us the direction is because it gives us the angle at which r is oriented with respect to a. So a is something we already know where it's headed, where it's oriented. Now here we assume that it was oriented the east direction. Solving for this would give us a value for phi. That would mean that r is now oriented at 5 degrees from east, and that means that we know the direction of r. So this is a value for r cap or r hat, and this is, as you would have guessed, is the value for r modulus. So that is how you work out the resultant of two vectors. In the next video, we'll try to work an example. We'll actually take this case and try to work out what theta, what phi and r would actually be. So I hope this video helped, and all the best.